Welcome! This is Dr. Plague. If you've watched part 2 of my video on the composite TV signal, then you saw that I demonstrated my homemade sync separator circuit, and this did not use a prefabricated sync separator IC, such as the LM1881. In this video, I'm going to show you how I designed it using common components. And as a bonus, we're going to put this homemade sync separator to the test, and we're going to see if we can use it to turn this old oscilloscope into a composite video display monitor. This old scope has an actual CRT as opposed to a modern digital scope which has an LCD display. Now, this video is going to be mostly concentrated on circuit design and some of the math that I use to select components. So, if you're just interested in the results, then you can skip ahead to that part of the video. I don't know how well this will turn out, or if we can even get it to work at all, but in any case, this should be a fun and interesting video. So please, stick around. So, let's talk a little about a sync separator, sometimes referred to as a sync stripper. What does it do? Let's watch a quick excerpt from my previous video where I explained it. What we want is for it to take an input, in this case, it will be a composite video signal, and it will provide an output. Specifically, the output will be an inverted version of the sync pulses from the input signal. And I'll make it a 5-volt logic level output. So if we have a composite video signal like this at the input, the output will keep just these negative pulses and invert them using 0 and 5 volts. I'll call this a sync separator, since it separates the sync pulses from the composite video. Now, if you haven't seen my previous video, then you might want to go back and watch the whole thing before continuing with this video. I'll place a link in the description. So now I'm going to go through and explain to you what my thought process was when I designed this sync separator circuit. Now, I'm not saying that this is the only way to design a sync separator. This is just how I designed it, based on the parts that I had on hand. And unfortunately, my design uses 3 power supplies, plus and minus 12 volts and plus 5 volts, which isn't a problem for me since my main supply has 4 channels. There's no reason you couldn't come up with your own design that uses just one supply. Actually, if you want to build this circuit and don't have access to plus and minus 12 volts, then you could probably get away with using a couple 9-volt batteries. Just be sure to connect them correctly. You would want to connect the negative lead of one battery to ground, then the positive lead of that battery to the plus 9-volt rail. Then connect the positive lead of the second battery to ground and the negative lead of the second battery to the minus 9-volt rail. You can then get 5 volts from the plus 9-volt rail by using a 7805 regulator or something similar. Now, beware that if you do use 9 volts, then you might want to change some components, since you will be out of spec from the recommended operating conditions. But I did try plus and minus 9 volts without any changes, and everything worked fine for me. There are 12-volt A23 batteries, which are similar in size to N cells, but they probably don't have the current capacity for this circuit, so I wouldn't recommend them. I also would not recommend using automotive or motorcycle batteries, unless you have some way to limit the current in case you accidentally miswire something. Those things can put out a ton of current. The nice thing about the power supply that I am using is that I can limit the current output in case something goes horribly wrong. Now we know what the sync separator does. It separates the sync pulses from a composite video signal and inverts them using a 5-volt logic level output. And bear in mind that the 5-volt logic level output is not mandatory for a sync separator. It is just the spec that I am specifying for my design. So now let's start the design. The first thing I want to do is to add a proper termination resistor to the input of our circuit to simulate the 75 ohm input impedance of a TV. So I'll just add a 75 ohm impedance matching resistor from the input signal to ground. You see, many devices that output a composite video signal will require the proper input impedance. For example, the video generator that I designed will use that 75 ohm input impedance as part of a voltage divider to get the proper voltage levels at the input. I suspect that this Blu-ray player does the same thing, because if you look at the composite video signal from it without the 75 ohm resistor, you'll notice that it sits at around 2.6 volts, and you can't see the video signal at all. Here it is with the resistor added in, and this looks like what we would expect. Other devices will also require 75 ohms to give you the correct voltage levels. Here is an example of a signal coming from an old VCR without a 75 ohm resistor. Notice that its amplitude is too high. The sync pulses should be about 286 millivolts, but without the 75 ohm resistor, they are around a half volt. If I add in the resistor, you'll notice that we now get the amplitude that we expect. The next thing I want to do is to add a little filtering to the input signal to help eliminate any 3.58 MHz chroma color signal. I'll call this a chroma filter. And I'll just design a simple low-pass filter using a resistor and a capacitor. We want to make sure that the sync pulses get by, which occur at a maximum rate of 31,500 times a second for the double frequency VSPs and EPs. We need to get at least to the 5th harmonic, which would be 157.5 kilohertz. But we also want the cutoff frequency to be well under 3.58 megahertz. So I'll choose 500 kilohertz for the cutoff frequency. I'll also choose a common resistor value of 680 ohms. Now, to calculate the capacitor value, we can use the formula for the cutoff frequency, which is 1 over 2 pi RC. Rearranging this gives us capacitance equaling 1 over 2 pi R times the cutoff frequency, and this gives us about 468 picofarads. So I'll just use the closest common value, which is 470 picofarads. Let's add that on the breadboard. And here's the original signal in yellow and the filtered signal in blue. Notice how most of the high-frequency content is filtered out. Now, I'm going to start from the back end, and we know we want an inverted 5-volt logic level output, so I'll just add a 5-volt Schmitt trigger inverter. Specifically, I'll be using a 74HCT14. This means that to get from the output of the chroma filter to the input of the inverter, we just need to detect the sync pulses in the video signal. We can do this by using a comparator. And we can make a simple comparator out of an op-amp. The way the comparator will work is that we will create a reference voltage with a voltage divider made out of resistors. Then, if the voltage of the composite input signal is above the level of the reference voltage, the comparator will output a high voltage. Else, it will output a low voltage. So, we need the reference voltage to intersect the sync pulses. But we have one major problem. The input signal could have a DC offset, which could place the sync pulses above the reference voltage. How can we handle this unknown DC offset? Maybe we could use an AC coupling capacitor? But the big problem there is we don't know what the amplitude is of the luminance signal, and therefore the sync pulses could be all over the place. We need some way to line up the sync pulses to a particular voltage level. To do this, we can use a clamper circuit. But first, consider that the sync pulses are only about 286 millivolts. That is not very large, and the noise on the breadboard could easily be close to that, so I want to amplify this a little before sending it to the clamper. For this, I'll use an op-amp with negative feedback. I'm going to use a TL082 op-amp. It's not the best choice, but it's what I have on hand. There are 2 op-amps in each chip. The slew rate is decent with 13 volts per microsecond. I would not use a 741 op-amp since it has a ridiculously slow slew rate of only 0.5 volts per microsecond. Bear in mind that the TL082 only has a guaranteed common mode input voltage no closer than 4 volts to each supply rail. But typically, you can get as close as 3 volts to the negative rail, and you can go all the way up to the positive rail. Also, it is recommended to use at least 10 volts for the TL082, which is no problem if we use plus 12 volts and minus 12 volts, which gives us a total of 24 volts. The input voltages can go all the way to the rails, as long as they don't exceed plus or minus 15 volts. Now, I'll configure the op-amp as a non-inverting amplifier with a gain of 4. The gain will be 1 plus the value of this resistor divided by the value of this resistor. 3K divided by 1K is 3, and adding 1 gives us a gain of 4. And I'll use plus and minus 12 volts. Let's add this to the breadboard. And here's the current result on the oscilloscope with the original signal in yellow and the filtered amplified signal in blue. Notice that the amplitude of the blue trace is about 4 times larger. Now I'll add in a clamper circuit. We can make a clamper circuit with an op-amp, so we can use the second op-amp in the TL082 for the clamper. This is going to be a positive clamper, since I'm going to clamp the bottom of the video signal up to a certain voltage. Since we're going to shift the level of the signal upwards, I'll use an AC coupling capacitor so we don't disturb the signal coming in. Now I'll configure the op-amp similar to a voltage follower, but I'll insert a diode at the output like this. I'll just choose a 1N4148 diode. Now, all we need to do is to apply the voltage level that we want the bottom of the video signal to sit at to the non-inverting input of the op-amp. We can use a resistive voltage divider for this. I'll choose 10K and 4.7K to get us close to 4 volts. And optionally, we could throw in maybe a 10 megohm resistor right here to help it settle down more quickly. We'll add this to the breadboard. And here it is on the scope. The yellow trace is the original input signal. Blue shows the signal after the clamper, and pink shows the non-inverting input of the op-amp, which is the level we are clamping up to. Notice that the entire signal in blue is above the pink. Well, there is a very slight overlap, but that's no big deal. Now, all that is left is to add in the comparator and adjust its output level for the input of the inverter. To make a comparator, I'll just use another TL082 and connect its positive rail to 12 volts and its negative rail to ground. Beware if you're using 9-volt batteries that the supply voltage will be slightly out of spec, since it is recommended to use at least 10 volts. So you might want to use a different op amp for this. But like I said, I did try 9 volts and it worked for me. Now, I'll just send the output of the clamper to the non-inverting input, and I'll provide a reference voltage to the inverting input. Again, I'll use a resistive voltage divider for the reference voltage. I'll use the same 10K and 4.7K that I used over here, but I'll add in a 2K potentiometer so I can set the reference voltage a bit higher to intersect the sync pulses. Let's breadboard this. We can view both inputs of this op amp on a scope to adjust the reference voltage in pink until we intersect the sync pulse in blue at a good level. Now, the output voltage of the comparator will be somewhere between 0 and 12 volts, which is too high for the inverter, as can be seen here in blue. So I'll just add in another resistive voltage divider using 10K and 5.1K. This will guarantee that the signal into the inverter will be under 5 volts, and it should be able to cross both thresholds. The signal before the voltage divider is in blue, and after the divider is in pink. I'll add the inverter to the breadboard. It would be good practice to tie the inputs of any unused gates to either ground or 5 volts, even though I haven't done this. You've probably heard the old adage, do as I say, not as I do. Also, it would be a good idea to throw in some capacitors on the power rails to ground to help filter them out. Again, I haven't done this. And there we have it. This is the black box sync separator circuit that I used in part 2 of my video on the composite video signal. You can see the composite video signal in yellow and the 5-volt logic level output of the sync pulses in blue. Now, to complete this sync separator, let's add in the integrator and differentiator from the last video. And now we can represent this whole circuit with another black box that takes a composite video signal as its input and has 2 outputs, a vertical sync and horizontal sync. Finally, let's move on to the exciting part of this video. We're going to try to display a video on this old oscilloscope. I do not know how this will turn out. I could succeed, I could fail, I could blow out the oscilloscope. Oh, the excitement is too much. Now, why am I using this old scope as opposed to one of my new digital scopes? You see, many of these older scopes have what is known as a Z-axis input, or in the case of this oscilloscope, it's called a Z-mod, and it's on the back of the scope. Z-mod simply stands for Z-modulation. And what it does is it allows you to control the brightness of the electron beam with a voltage level. Then, if you set the scope for XY mode, you have complete control of the electron beam. You can control the X and Y positions of the beam with the two main channels of the scope, and control the brightness with the Z-Mod input, just like you can control the CRT of a TV. Most modern digital scopes do not have a Z-axis input, so this would be impossible to do on my digital scopes. There is one digital scope that I know of that has a Z-axis, and I believe that is the Tektronix 5 Series MSO. If you know of any other digital scopes that have a Z-axis input, then please leave a comment. Now, let's play around a little with this scope to see how it works. This is a 2-channel Philips PM3070 100 MHz scope. Bear in mind that this is an old scope, circa 1988, and it is well used and not in the best of condition. But it's the only working scope that I have that has a Z-axis input. Actually, the power switch doesn't even work anymore. I had to go inside and modify it so that it's permanently powered on whenever it is plugged in. This scope has seen better days. I'll first turn off the text. Now, to set the scope to XY mode, we need to press this button for X deflection. Now, I'll apply a voltage to the first channel, A. Note that the channels on this scope are named A and B. Notice that the beam moves diagonally up and to the right when we increase the voltage, and this is not what we want. So I'll press the AB button, and yeah, that's not what we want either. Let's press AB again, and the third time's the charm. As we increase the voltage, the beam moves to the right. So channel A controls the beam from left to right. We can use channel A as our horizontal deflection input. And if we connect up channel B, we'll see that as we increase the voltage, the beam moves up. But that's not quite what we want. We want it to move down as we increase the voltage. So I'll just press this Add Invert button to change that. Now channel B controls the beam from top to bottom. We can use channel B as our vertical deflection input. Next, let's check out the Z-Mod input. And this is very touchy. It looks like we have full intensity when we are at or under about 0.7 volts. And it appears to disappear around 1 volt or so. So this input is extremely sensitive. But if I increase the intensity, it doesn't completely disappear until we get around 1.3 volts. But this is just a little less than the luminance in a composite video signal. However, when we end up spreading the beam over the entire screen, this luminance voltage range will appear to be even less, so we'll probably need to attenuate the luminance signal slightly. You can see that we can move the electron beam up, down, left, right, and we can change the intensity. That's all we should need to be able to display a video on this scope. So now that we know what signals we need to control this scope, let's design some circuits to produce these needed signals. For the horizontal and vertical deflection voltages, we can design a couple voltage ramps, which will be retriggerable using the outputs from our sync separator. There are many ways we can create a voltage ramp, but since I already made a video on the 555 timer, let's use 555 timers to create the voltage ramps. I'll set the 555 up like this. Now, the way that this will work is that this capacitor will charge up using the current from this resistor. The capacitor will keep charging until the threshold voltage on pin 6 reaches 2/3 VCC, which in this case, VCC is 5 volts. When pin 6 reaches the threshold voltage, then the capacitor will discharge to 1/3 VCC before it starts charging again. We can use the voltage on the capacitor as our ramp voltage. So we can ignore the output on pin 3 of the 555 timer. And I'll AC couple the output through a 0.1 microfarad capacitor. But there is a small problem with this. The voltage across the capacitor will not charge up linearly when using a resistor to charge it. So we won't let it charge all the way up and use less of the voltage curve so that it appears more linear. Specifically, I'll charge the capacitor up to 1 volt. I'm going to pick a resistor value of 10K. Now, for the vertical deflection ramp, we want to choose a capacitor value that will charge up 1 volt in 1/60th of a second, which is approximately 16.7 milliseconds. So, let's look back at my math behind the 555 timer formulas, part 1 video. And this is the formula that we'll use to calculate the capacitor value. I want the initial voltage to be 1/3 VCC, and we'll charge the capacitor up to 1/3 VCC plus the amount we want to charge it. I'll call that V. I'll divide both sides by VCC, then I'll multiply each side by 3. I'll subtract 3 from each side, then subtract 3 from 1, which gives us -2. Now I'll negate each side and divide each side by 2. Then I'll replace the 1 with 2 VCC over 2 VCC and simplify that to 2 VCC minus 3V all over 2 VCC. Next, I'll take the reciprocal of each side, then I'll take the natural log of each side, which will cancel out the E. I'll multiply each side by C and divide each side by this natural log expression. And this is our formula for the capacitor. For the vertical deflection circuit, VCC will be 5 volts. We want to charge the capacitor up 1 volt, so V will be 1. We already said R is 10K, and the time for charging will be 16.7 milliseconds. This will give us approximately 4.68 microfarads. And the closest standard value will be 4.7 microfarads. So we'll use that. And I'll send the vertical sync from our homemade sync separator to pin 6 of the 555 timer to re-trigger the ramp. I'll wire this up on a breadboard. And I'll add a bypass capacitor from 5 volts to ground. Now let's send a composite video signal into this and look at the ramp on an oscilloscope. Again, the original signal is in yellow with the vertical sync pulses here, and the ramp voltage is blue. Looks decent so far, but notice that the diagonal ramps are not quite straight lines, but rather slightly curved. In other words, not perfectly linear, but close. Now, for the horizontal deflection circuit, we'll use the same 555 timer circuit with a few changes. I'm going to give the horizontal sync from the homemade sync separator a DC offset using a resistive voltage divider with a 0.1 microfarad AC coupling capacitor. I'll choose 10K and 15K for the resistors so that the DC offset is just under the threshold voltage for re-triggering. And since this input is a voltage spike, I want to be a little cautious and up the supply voltage to 12 volts so the spike doesn't exceed that. Now to calculate the capacitor, we'll use 12 volts for VCC, 1 volt for V, 10K for R, and 63.5 microseconds for the time. And this gives us about 47.6 nanofarads. So I'll just use a 47 nanofarad capacitor. Notice that this circuit will retrigger off of all the horizontal sync pulses, even all the double frequency pulses. This is fine. We don't need to ignore some of the pulses. Let's wire this up on a breadboard. Let's add a bypass capacitor from 12 volts to ground. Again, let's send a composite video signal into this and look at the ramp on an oscilloscope. We'll zoom into this. This one is a little more linear due to the higher VCC voltage of the 555 timer in the horizontal ramp circuit. And both of these ramps look decent, but we can actually do better than this. If we could increase the voltage amplitude of these ramps, then all the noise in the circuit will appear to be less in relation to the size of the ramps. So, to increase the voltage, we would need to replace the resistors that are charging the capacitors with constant current sources. This will make the voltage ramps more linear. I'll use Wilson current mirrors, which look like this. I'll use 2N3906 PNP transistors. In this configuration, the current through this resistor will be mirrored at the collector of this transistor. Since we are increasing the ramp voltage, I'll increase the supply voltage of this 555 timer to 12 volts. And because of that, the threshold level will increase. So I need to add a DC offset to the vertical sync voltage coming from the homemade sync separator. I'll use a 10K and 15K resistor divider to do this. Now I'll just replace this 10K resistor with the Wilson current mirror. Next, we need to figure out what value of resistor to use in the current mirror. To do that, we need to know how much current we need to charge the capacitor to, let's say, about 6 additional volts. Now, the voltage across a capacitor is the charge, Q, divided by the capacitance. And the charge is current, I, times time, T. So, V equals I times T over C. And we can rearrange it so that I equals C times V over T. And if we want 6 volts in 16.7 milliseconds, knowing that our capacitor is 4.7 microfarads, then the current I will be 1.69 milliamps. The value of the resistor will be the voltage across it divided by 1.69 milliamps, and we have 12 volts minus 2 diode drops, which gives us a resistance of 6,272 ohms. I'll just choose a 6.8K resistor. Now let's add a Wilson current mirror to the horizontal section. To calculate the resistor, I want to charge the 47 nanofarad capacitor about 6 additional volts in 63.5 microseconds. So the current needed is about 4.44 milliamps. Then our resistor will need to be about 2,387 ohms. So I'll just choose a 2.2K resistor. Let's make this change to the breadboard, but just as a note, technically, we would want to bond these two transistors in each current mirror together with heatsink compound to maintain equal temperatures. But I'm not going to do that. And the extra transistor in the Wilson current mirror helps to overcome this by keeping these two transistors close to the same voltage drops. This should be good enough for our purpose. Now, let's look at the ramp outputs on an oscilloscope. The yellow trace is the original signal, the blue trace shows the ramp for the vertical deflection voltage, and the pink trace shows the horizontal deflection voltage, which I'll zoom into. You can see that we get a much more linear ramp with a higher voltage. The voltages aren't exactly 6 volts, but close enough. This is due to several factors, including the approximate resistor values, transistor matching in the current mirrors, and tolerances. Finally, we need to come up with a luminance signal to vary the brightness of the electron beam in the oscilloscope. Since the oscilloscope beam darkens with more voltage, we need to invert the composite video signal. I'll use a 2N3904 NPN transistor to do this. Due to the sensitivity of the scope's Z-mod input, I fear that the luminance in the composite video signal is a little too hot, so I want to attenuate it slightly. I'll choose 220 ohms and 330 ohms for these resistors, which should add a little attenuation. If you're trying this out, then you might want to add a potentiometer in for the 220 ohm resistor to adjust for your scope. I'll AC couple the composite video signal into this using a 0.47 microfarad capacitor. Then I'll add a DC offset bias voltage with a 10K and 4.7K resistor. I want to be able to adjust the DC offset of this attenuated signal, so I'll just add in a negative clamper circuit. A negative clamper is built the same as a positive clamper, except you just reverse the direction of the diode. For the reference voltage, I'll just use a 10K resistor and a 2K potentiometer. And since I'm out of TL082s, I'll just use an NE5532 op-amp for this, since I have a few of them lying around. Since this op-amp contains 2 op-amps per package, I'll just create a voltage follower buffer with the second one. And this will be our luminance output. Let's add this to the breadboard. And let's take a look at the output on a scope. The yellow trace shows the original composite video signal. The blue trace shows the luminance signal that we created, and the pink trace shows the reference voltage on the non-inverting input of the op-amp. See how I can adjust the DC offset with the potentiometer? The blue trace clamps down to the pink trace, and I'll set it to about here. Now, I think we are ready to connect this to the old oscilloscope to test this out. We have all 3 signals that we need. We have the horizontal ramp, which will connect to channel A, the vertical ramp for channel B, and the luminance signal for the Z-mod input. I'm going to attempt to play my part 2 video on the composite TV signal on this oscilloscope. What I did was put the video on a USB memory stick, then plug that into a Blu-ray player, and I'll use the composite video output from the Blu-ray player to send the video to my circuit. Now, I did have to crop the video to a 4:3 aspect ratio to display properly on this scope. So first, I'll connect the horizontal output and adjust the size. Then the vertical output. And finally, I'll add both. Then I'll increase the intensity. The last thing is to connect the luminance signal. Oh, wow! This is a pretty good image. I'm actually quite impressed with this. Honestly, I wasn't expecting it to be this clear. You know, I thought I would get some kind of an image, maybe a blurry one, but this is better than I was expecting. We're using external circuitry that could pick up a lot of noise. I have fairly long, maybe 4-inch wires connecting to the scope probes, and each of those can act as little antennas that pick up noise. So yeah, I'm impressed. There we are on the bikes. The text appears legible. There I am. And there's Mrs. Plague. I can even make out the text in that screenshot. Nice. Yeah, I'm very satisfied with this. I could actually watch a video on this without too much problem. The highlighted text looks good too. There's the VCR, and how about that? A scope on a scope! Where else can you find this kind of entertainment?
Wow, I have to admit, that was pretty cool, even for you.
I guess I'll take that as a compliment. Just for comparison, I connected the first 555 timer circuits up, the ones without the constant current sources, and just the 10K resistors for charging the capacitors, just to see the difference. And you can definitely see the vertical nonlinearity in this. Wow, compare that to the constant current sources. Let's do a side-by-side. Notice how the one without the constant current sources becomes more squished towards the bottom. Also, there's a little more noise in it due to the signal-to-noise ratio of the lower ramp voltages. You can really notice the nonlinearity when the camera scrolls up the front of my bike. Let's see that again. Can you see that? Rewind if you didn't. So this does work without the constant current sources, but not nearly as linear or sharp. Now, if you want to try making this a little more linear, and you don't have the parts to make a constant current source, then you could try increasing the voltage of the vertical 555 timer from 5 to 12 volts, and increase the capacitor from 4.7 microfarads up to 10 microfarads or so. You would still need to use a DC bias voltage for the vertical sync voltage coming from the homemade sync separator, such as the 10K and 15K resistors I used in the horizontal deflection circuit. Just as a side note, one thing I've noticed is that the image on the scope looks much better in person than when I take a video of it on a camera. Using a camera to capture a CRT image is very difficult due to the scan lines and the frame rate of the camera. Maybe, just for fun, in a future video, I might try redesigning this with 741 op amps, just to see if we can get anything to work at all with them. Well, that's all I have for today, and this video has become a lot longer than I hoped for. But I do hope you found this fun and interesting, so please peck at that like button. Also, please leave any comments you have and consider subscribing if you haven't already done so. Thanks for watching, and I'll see you next time, right here on Dr. Play.